Okay, so for the next example, we're going to determine the homology of the projective plane RP2. So let's just recall what RPN is, right? So RPN in general, this is SN mod equivalence relation, where we introduce the equivalence relation where U and V are related if and only if they're plus or minus each other. Okay. And then we form the quotient, and that's called RPN. Okay, so in particular, RP2 is S2 mod this relation here. So here's a sphere RP, here's a sphere S2, and so we've got any point U here, and then you've got your minus U there, and these kind of get glued together when we form RP2. But notice, yeah, and so in particular, if we've got maybe a point V on the equator, then that gets glued to the point minus V over there. And there's another way to represent RP2, which you might be more familiar with from the knots and surfaces course, for example, because everything in the upper half plane, in the upper hemisphere gets glued to its kind of counterpart down in the lower hemisphere, we don't really need the lower hemisphere. Okay, we can just throw away the lower hemisphere, and we've just got the upper hemisphere. But then we still got some gluing going on. You've got we just keep the upper hemisphere, the closed upper hemisphere, including the equator, and then these points V and minus V that are still on the equator, they get glued together. But now once we've just got the upper hemisphere, right, you can flatten that down. The upper hemisphere is homeomorphic to a disk like this, and we're gluing points on. Gluing each point on the disk to the opposite point. So we're going to call this point here A and this point here A, and this path here that goes around the edge V. So there's V. Yeah, sorry, I called this A and I called this one A as well because in the projective space we're gluing this one and this one, so they're the same. And then we've got this path V which goes around the edge from this A to A, and of course. Yeah, this is the same edge. This is the same edge, right? Because every point in the upper semicircle gets glued to the corresponding point on the lower semicircle. So this is V, and this is just the same after gluing it. Right? And so as before, we're going to we want to calculate the homology of RP2. We're going to divide it into the union of two open sets. So our U is going to be this bit here, where we've kind of cut a hole in the middle, but we still left a sort of band around there. So then let's just put the markings back in. So we've got our edge V, kind of two copies of the same edge appearing in this picture. Okay, that's our U, and our V is just going to be a disk in the middle, and it's going to slightly overlap with this, so as to ensure that U union V is the whole of RP2, and so that means that the intersection is going to be like a thin annulus like this. Okay, so this disk like this, and it intersects with there, and so you just get a circle like this. Okay. And we're going to draw another edge, another path, a loop in U intersect V. This one we're going to call little u, runs all the way around this circle. So U intersect V is that's going to be homotopy equivalent to S1, and homology of U intersect V is therefore going to be, we've got a Z and then just ZU here. And then V is contractible. So the homology of V, we've just got a Z in degree 0 and nothing else. And then we need to think about this. What's this U? That's less obvious. So we'll have a look at this picture here. Okay, so this is basically our U. except that there's U. This is the picture that we drew of U, but there's some gluing going on, right? You have to glue this outer edge to itself. You have to glue all the points along here to the points along here, and so on. And we can kind of see how that works. We sort of wrap it up like this. Okay, and then we need to glue. So we marked half of the edge in green, half of the edge in red, and now the red bit and the green bit are getting glued together, and we get this. So we get a Möbius strip. Okay, so this we had the marked edge around there. That becomes the sort of central line of the Möbius strip, and you see. We've got sort of kind of fringe to one side of the arc and a fringe to the other side of the arc, and when we glue it together, we get kind of fringes on both sides of the marked circle. Right? And now those fringes form this Möbius strip like this. Whereas what we had, this is the inner circle here. That becomes this kind of outer edge of the Möbius strip. So this is homeomorphic to the Möbius strip, and therefore homotopy equivalent to S1. Okay, let's maybe also just explain that. Homotopy equivalence okay, I mean here's your Möbius strip, and you can just you've got the inclusion of the circle, and then this kind of movie is showing your homotopy from the identity down onto the circle. So it's showing that the inclusion of the circle is a homotopy equivalence. Okay. And so we conclude the homology of U. Well, as usual, you just got the Z in degree 0, and then you've got your Z V in degree 1, and then zeros. Okay. So that's the homology of U, V, and U intersect V, and we want to calculate the homology of U union V, which is your RP2. Okay, so kind of key point of that again is that we've got this inclusion from U intersect V going to U. Okay, and U intersect V, remember, was this kind of annulus here, and which we've got a loop U which goes once around here, and then our U intersect V was a kind of slightly bigger thing. Here's our U. We had the base point A here, and you've got V going here, and then this was also V because everything is glued. Okay, so and then we can draw the loop U in here again. So U is homotopic by a loop homotopy in the space U. So if you push it outwards onto the edge, well, it goes around this V and then around this V. And those V's are both the same, right? Because they get glued. So this gets it's homotopic to V star V. So in the homology group, the I lower star of U, that's the same as the homology class of V star V. And by a thing that we discussed previously, the join of paths is corresponds in homology to addition. So this is square bracket v plus square bracket v to twice square bracket v. Okay. Okay. So now we do the truncated Myvie-Torres sequence. So we've got our H3 of u intersect v, H3u plus H3v to H3 space RP2, and then it goes around, you get the same thing with H2. And everything's connected. We can do a truncated version of the Myvie-Torres sequence, so we just have a 0 there. And let's just record over here what we know about the homology groups. Homology of U, U was this. We said that's homotopy equivalent to a circle, and the we just get Z and ZV. Homology of U intersect V. So U intersect V, again, this is just a homotopy equivalent to a circle. So this is we've got Z and then ZU and everything, and then V was contractible. V was just like a disk, so that's contractible. Homology of V is just Z and then zeros. Okay, and these Z's in degree 0, they're not appearing here in the truncated Myvie-Torres sequence. So everything that's the only thing that's interesting here. So we've got this group here is 0, right? And this group here is 0. Here you've got H1U plus H1V. Okay, so you've got H1V is trivial. So here you've just got ZV. Here you've got ZU, and then here and again. Higher homology of U intersect V, so U intersect V like so there's a circle, so these groups are all 0. And then over here we've got the homology of RP2, which is the thing that we're really interested in. And this was mapped with I lower star, so U is going to 2V here. Okay. And this is this is basically just multiplication by 2 on Z, so this is an injective map. So the kernel of I lower star is 0, and that's the same thing as the image of this delta. Okay, but you've got a 0 here, right? So that means exactness means that this delta is injective. Delta is injective, but the image of delta is 0, so that means that delta is the 0 map, and this H2 RP2 has to be true. Okay, so well, actually, let's look at H1 of RP2. Okay, so here you've got a Z. This map here has got to be surjective because you've got a 0 there, and then the kernel is the image of this I lower star, which is generated by 2V. So that's isomorphic to Z mod 2. Okay, the image of V is a generator, the 2V goes to 0. Okay. And H2 of RP2 is also 0 by its kind of slightly more complicated argument, because this I lower star is injective, so the image of delta is 0, and delta is also injective, so the actual group has to be 0. And then by an easier argument, this H3 is trivial just because it's sandwiched between this 0 and this 0. And then in exactly the same way, you could just push this sequence higher up. Okay, so higher groups are also trivial. So our conclusion is the homology of RP2 You've got a Z, then a Z mod 2, and then zeros. Okay, so that's our first example of a space of a homology group, which isn't just Z to the K for some K. Okay, so there's the homology of RP2.